In this presentation, I'll be giving an introduction to wind turbine. Now let us see wind energy. Wind is the flow of air on very large scale, and wind is created due to the pressure difference in Earth atmosphere. Because of the atmospheric pressure difference, the wind is being created or generated. And wind blows from a region of high atmospheric pressure to low atmospheric pressure, and the difference in pressure is because of the two facts. One is the earth surface is not uniformly heated by the sun. Second reason is that earth's rotation. These are the two reasons why the pressure difference comes, and that causes airflow. And essentially the wind energy is a byproduct of solar energy available in the form of kinetic energy of air. And this kinetic energy of the air can be extracted by using wind turbines, and it can be transformed into electrical energy. And wind power is a very clean, sustainable, and renewable source of power. Continuing the wind turbine introduction, a device which is used to convert the kinetic energy of the wind into electrical energy is known as wind turbine. And wind is the movement of air mass from area of high pressure to the area of low pressure, and the energy associated with the mass movement, the kinetic energy, is called half mv square, where m is the mass of the air and v is the velocity of the airflow. This is the kinetic energy associated with the air movement, half mv square. Then air flowing through the wind turbine is treated, that can be treated as a segment. Looks like a horizontal cylinder, just like it can be treated as a cylinder like this one. And the mass airflow per unit time, that is mass is equal to, that is rho is the density of the air, and a is the cross sectional area, and v is the velocity of the air, and rho into a into v is the mass of the airflow per unit time, rho av, and where rho is the density of the air and a is the surface area of the cylinder, the surface area of the cylinder, cross-sectional area of the cylinder, and v is the wind velocity. Therefore, this is the mass, and if you substitute in this equation, you will be getting the kinetic energy of the wind, that is given by half mv square, which is equal to half into m equal to this one, rho into a vq. Therefore, the kinetic energy of the wind equal to ek equal to half rho avq. Now continuing the wind turbines introduction, that is kinetic energy of wind, already we have seen, it is equal to half into rho into avq. And the kinetic energy of the wind energy, that depends upon the three factors. One is the density of the air, second is the surface area, A, capital A, and v is the velocity of the air. These are three factors that controls the wind energy. Therefore, the conversion of kinetic energy of the wind into electrical energy using the wind generators, and the wind kinetic energy in the wind kinetic energy in the wind is converted into electrical energy by the device known as wind turbine coupled to a generator. Therefore, this is a wind turbine with coupled to a generator. Here, this is the wind turbine system, which the air is or wind is hitting these plates, and due to the rotation of this one, that is transferred using a transmission system, or there's a gearbox system is there, and that is this one, that is transmission system, and that transmission system transmit this mechanical rotation into the generator, and that electrical system, it is the electrical system that because of the rotation of this, of course the prime mover or the generator generates that voltage, AC voltage, that is connected to the grid, existing grid that is connected. So this is the basic, just say block diagram of this wind turbine system, or wind turbine with a generator. Therefore, this is the wind power. This is a it's captured, mechanical power, that is and that mechanical power again that is converted in electric power using this generator that is connected to the existing grid. Therefore, these are the turbine blades, and wind is hitting on this turbine blade. This is rotating, and that is transmitted, and that is using the gearbox mechanism, that can reduce the speed of that one, or that will change the speed by the gearbox mechanism that is coupled to the generator, and AC voltage is generated that is coupled to the synchronized to the existing power system. Now continuing this wind energy conversion system, WECS it is called. For that, it's a block diagram which is shown here. For wind is falling, there's a wind turbine, and the wind turbine that is through a transmission gearing mechanism that is connected to the generator, and the generator is generates the AC voltage that is connected to the utility. Therefore, there's a that is mechanism to synchronize and to connect to the existing grid. That's mechanism that is called contractor or soft start. That is again here generator voltage will be AC, and that is converted into DC, and then again DC is converted into AC, or rectifier plus inverter setup is that is a power electronics based system, and again that is connected to the existing unit grid. And to control, there's a mechanism of course there is a computer based control is that controls this system as such. Therefore, this is a block diagram representation of wind energy conversion system, and that is as a schematic diagram as that what all things are there, and there is a blades. There's a hub is there. Hub is the component that usually holds the blades and connects them to the main shaft of the wind machine. Therefore, that is the hub is the blades, and here there is a motor shaft as there. Therefore, there is a big gear box mechanism is there, and there is a braking mechanism that is connected to the generator. This is of course that is the tower over which this setup is made, and this is the mechanism of a schematic diagram of a wind energy conversion system, WECS. Now continuing the wind turbine introduction, as there's a term what we call Betz limit, derived from the conversion of mass and momentum of airstream. The term used in relation with the extraction of the wind power. That is Betz limit is there here actually. Betz limit is the maximum power that can be harnessed or that can be extracted from the wind, and according to Betz law, it says it is only possible to extract 59% or 16 by 27% or 59% of the kinetic energy from the wind. As per the Betz law, it is only 59% is possible to extract the of the kinetic energy into the wind. From the wind, it can be possible to extract 59% only. For Betz law is also states that any wind turbine could convert more than 59% of the kinetic energy into the mechanical energy for turning the turbine. That's maximum limit is 59%. For Betz coefficient, that is 16 by 27, that's called 59%. And as per the Betz statement, the maximum power that can be extracted by the wind turbine, that is EK max, maximum that is equal to 0.59 or 59% of already we have seen half rho AVQ. Therefore, this is the maximum possible power that can be extracted by the wind turbine. Continuing the introduction, wind turbine, we have seen 59% of the theoretical value at standard condition, neglecting the losses. That is, here in practical condition, wind turbine can attain maximum value 70 to 80% of the Betz limit. Only in practical case, it can attain only 70 to 80% of the Betz limit. That is 70.7 to 0.8 of this much. Or that scheme seen that here taking 70% as a practical Betz limit here. If you take 70%, the maximum kinetic energy that can be extracted on that one is equal to 0.7 into again 0.70%, 0.7 into already 0.59 into half of rho AV cube, or you'll be getting 0.41 half of rho AV cube, or this is called CP, or this is called CP, which is called coefficient of power, CP into half rho AV cube. Therefore, the coefficient of power CP equal to the product 0.7 into 0.59, which is equal to 0.41. For the maximum conversion of the wind power is 70% of the Betz limit, which is equal to 0.41 times half rho AV cube, or CP into half rho AV cube. Now, the coefficient of power CP that can be defined as this one equal to the electrical energy produced by the wind turbine divided by the total energy available in the wind. That ratio we call it as the coefficient of power Cp, which is equal to 0.41, or we'll get only 41 percentages. Here you can say that it is only a 41 percentages getting. The wind energy is only 41 percentage or 70 percentage of the this limit or Betz limit. Therefore, the Cp can also be called, that's also called power coefficient of the wind turbine. Cp can also be called as power coefficient. And thus, wind turbine converts 41 percentage of the available wind energy into electricity. That is, it is the efficiency of the turbine. That is, 41 percentage the maximum possible of the 41 percentage of the available wind energy can be extracted. Therefore, that is here. Wind energy of 100% is available, it is only equal to 41 percentage. Now power delivered from the wind turbine. The power delivered from the wind turbine, that is in watts, equal by rho, P equal to 0.5 into Cp into rho into, this is pi r square, that is A into V cube. This is A. Rho A V cube means pi r square is A. Therefore, 0.5 Cp into rho into pi r square V cube is the power delivered from the wind turbine, where Cp is the coefficient of power and rho is the air density in kilogram per meter cube, and R is the blade length in meters, and V is the wind speed in meters per second. Therefore, this the power delivered, or the power delivered from the wind turbine is given by 0.5 Cp into rho into pi r square V cube. Now, this is a plot of a typical power versus speed characteristics. That is from this equation. This equation is, that is power versus speed characteristics. This is the power, it is the per unit value, and this is the speed as such, and for the wind turbine speed as such, and this is the wind speed. This is the wind speed, like that 15 meter per second, 13 meter per second, 11 meter per second. We can say that one. The power that can be derived from the turbine, that is for different wind speed, is plotted here versus the speed of the turbine. This is given here. You can see that one. The maximum power that can be extracted for different wind speed is, that is locus, is plotted like this one. That is this point. Therefore, if you see, for example, if the wind speed is equal to 15 meter per second, the maximum power that can be extracted, corresponding speed is given by the corresponding speed is showing this, the speed corresponding to here, that is the turbine. Of course, the wind turbine speed is that one. Therefore, this is a plot of the power that is derived from the wind turbine versus the speed of the turbine for different, of course, the air velocity, wind velocity. And the same shape here can get is, if you plot torque versus speed, same thing, torque versus speed, but torque is nothing but T into omega equal to power, or power torque T into omega equal to power, or torque equal to power divided by omega. If you plot that torque versus speed for different wind speed, that is same shape as that one, and this is the speed characteristics of the two blade propeller type rotor. This is the torque produced, and this is the speed of the turbine, and for different wind speed. Now we have to define certain ratios, like when we call it as tip speed ratio, TSR it's called. Tip speed ratio, TSR, it is the relation between the wind speed and the speed of the tip of the wind turbine blade, and that ratio we call it as TSR, or tip speed ratio, or that is represented by lambda, which is equal to tip speed of the blade divided by wind speed, or lambda equal to omega r, that is the wind speed in terms of angular velocity and into the radius of the rotor in meters, omega r divided by velocity v. Omega r divided by v equal to lambda, which is called tip TSR, or tip speed ratio. And tip speed ratio, TSR, has a significance related to the efficiency of the turbine. That efficiency of the turbine, that is significant, that is affected by the TSR, or tip speed ratio, which is equal to tip speed of the blade divided by the wind speed, which is omega divided by v. The another parameter is that pitch angle of the wind turbine, that is represented by beta, pitch angle of the wind turbine. The pitch angle of the wind turbine blade is the angle between the blade's rotation plane and the tip of the line. That is the tip of the line and the this angle. That is, this angle we call it as, this angle is called that pitch angle. And it is a key parameter that affects the blade aerodynamic performance and determines the wind angle. That is, that will represents the, of course, the angle of attack as such. That is wind angle of attack. And this angle of attack changes the aerodynamic loads and receives wind flow on the and and that is related to the wind flow of the rotor. That is the this parameter is much important as that one. That is called pitch angle. That is pitch angle that's represented by beta. This angle. Now we have seen the already tip speed ratio TSR and pitch angle, and how that is related to the power coefficient CP. That is tip speed ratio TSR and of course the power coefficient, and for different pitch angle beta. That is, this is a plot of that one. That is, this axis is equal to y-axis is equal to power coefficient CP varies like that one, and this is a tip speed ratio lambda. And of course, for different pitch angle beta is that one. For beta and pitch angle, for the coefficient of power CP that expresses what fraction of the wind power is being extracted by the wind turbine. By what fraction of the wind power is being extracted by the wind turbine, that is represented by this power coefficient. Therefore, it is a function of tip speed ratio and pitch angle. For example, if beta is equal to, say, if beta equal to 0 as such, we can say that one, this blue dotted curve is that represents, that is power coefficient. That power coefficient, you can have the power coefficient of maximum this much if the tips ratio is this much, or that gives a relation between power coefficient and tip speed ratio for different pitch angle beta. Therefore, of course, CP represents the fraction of the wind power that is can be extracted from the wind by the wind turbine. Now let us see the relationship between tip speed ratio TSR and number of blades of the wind turbine. The tip speed ratio is inversely proportional to the number of wind turbines. Large number of wind turbines that will have a low tip speed ratio. TSR will be less if the number of blades are more as such. And the if the number of blades are more, the starting torque will be more high. The starting torque will be large, but tip speed ratio will be, that will be low value. So the starting torque is proportional to the number of blades of the wind. Therefore, as the number of blades increases, starting torque increases, but tip speed ratio reduces. Therefore, the wind turbine with a 2 or 3 blades will have a large TSR. Number of blades is less. It will have a large TSR, tip speed ratio, but low starting torque. That is inversely related. Therefore, high tip speed ratio permits the use of smaller and hence lighter gearbox to achieve required speed at driving shaft of the power generator. Therefore, high TSR ratio means that the, of course, high TSR ratio, the number of blades will be less, and of course, the torque produced is also the number of, the starting torque will be less and hence lighter, and gives to achieve the required speed at the driving shaft of the power generator. We have already seen the parts of wind energy conversion system as such, and this is the hub that connects the blades with the shaft here, and this is the main shaft is the, of course, gearbox is there, and that gearbox changes the, of course, the torque availability. Torque will be changing by this gearbox mechanism, and that is connected, of course, the braking mechanism that is coupled to the generator, and the generator generates the, of course, the power generation is done by this generator mechanism or generator. Therefore, that is here high speed shaft is that high speed is done by this gearing mechanism that will do the, of course, this mechanism will do the increase the speed. Of course, torque will be less and increase the speed. That is done by the gearbox mechanism, and that is these are the blades, and this is a tower, and therefore these are the different parts of the wind energy conversion system as such. And here wind turbine with 2 or 3 thin blades which rotates at high speed, providing electricity to many farms and beyond the reach of the power lines. This is the different parts of the this wind energy conversion system. Now let us see the different parts of wind turbine. Wind turbine has been shown here. First one is the foundation. Foundation, that is this one, number 1. It's the basement of the wind turbine on which the whole self weight of the wind turbine will come. It is normally under the surface and it cannot be seen it cannot be seen also. That's called the foundation. Below the surface it is. Second, that is this one, number 2 as such, to the electric grid. This is the connection from which the generated power is sent to the electric grid with the help of electric wires. That is to the electric grid, number 2. 3, that is number 3, this one. 3 is the tower. It is a supporting structure for nacelle and air and rotor. And the nacelle is placed above the tower. Tower is the assembly of number of cylindrical hollow structures which are assembled at the side. Wind farm, that is the tower. And access ladder, that is number 4, that is access ladder is there. And there will be a ladder inside the tower from the basement to the top so that one can get access to the nacelle for any kind of repair and inspection work. Therefore, that is the access ladder. That is the number 4. Number 5, that is yaw control. That is this one. That is this is number 5, yaw control. Since the direction of the wind keeps on changing with respect to the time, and the rotor should be placed in the direction of the wind to get maximum power output, this yaw control helps in changing the direction of the rotor and will place it in the direction of the wind. That is done by this yaw controller, number 5. And nacelle, that is number 6. It is a rectangular like structure that contains generator, controller system, cooler, etc. When yaw control activates, the whole nacelle is rotated in the direction of the wind. That is number 6. And 7, that is the generator. Generator, it is a unit responsible for the power generation. This is a generator that is responsible for the power generation. And anemometer. Anemometer is a device that is used for the wind speed measurement, and this data is being sent to the control system. That is, this is a anemometer which measures the wind speed. For these are the other components: yaw controller, nacelle, generator, and anemometer. Continuing the other parts of wind turbine here, that is 9, number 9, that is this one. This is used to stop the rotor that is rotating. That's a brake actually. Brake, it is used to stop the rotor, and that is, the rotor that is rotating. Usually brakes are applied when weather conditions are not good to generate the power, or the RPM of the rotor is above the normal speed, which may not be suited to the generator. Therefore, under that condition, we'll be applying the brake as such. Therefore, that number 9, that is the brake. Number 10, this is a gearbox mechanism. It consists of gears that increases the RPM of the rotor to suit to the RPM of the generator. Therefore, that increases the RPM of the increases the RPM of the rotor to which is suitable to the generator. That is done by the gearbox mechanism. That is represented by 10. And 11, that is the rotor blades. The rotor blades are there. That is rotor blades. Rotor blades are the rotating member of the wind turbine that makes the shaft to rotate, which is connected to the gearbox and then to the generator. Blades are of aerofoil shape, and length will vary from 30 meters to 80 meters approximately, depending upon the rated power of the wind turbine. That's called the blades as rotor blades. Then pitch control. It is used to change the angle of inclination or pitch angle, which are responsible for getting maximum efficiency. You have to control that. One pitch angle control is required that is that pitch control mechanism done by this system, pitch control. And the rotor hub, it is the one which holds the rotor blades, and it will also rotate along the blades. That is, a rotor hub is the 30. This is the rotor hub which is connecting the blades into the shaft. That is rotor hub. Therefore, these are the different parts of the wind turbine. That is 13 parts. I mean, already explained that one. This picture shows the different parts of the wind turbine, which I already explained. But as more to understand that one, the different parts of the wind turbine, that is the yaw drive is used to keep the rotor facing into the wind as the wind direction changes. This only applies to the wind turbine with a horizontal axis rotor only, that will be applicable. And the different parts of that one, of course, pitch control, the rotor is there, and wind direction comes here. Low speed shaft is there. There's a gearing mechanism is there that will be changing to the low speed into high speed, and that is connected to the generator, and that is certain control is the generator control is there. Of course, the anemometer to sense the wind speed anemometer is there, and here the nozzle and high speed shaft that is done by this gearing mechanism. The speed is increased. And here there is a yaw control drive application. This is a yaw control motor is the yaw control. Then in order to to keep the rotor facing into the wind as the wind direction changes, that is applicable to the horizontal axis rotor. Therefore, a yaw motor and yaw driver is the, of course, blades are the, and tower is the. Therefore, the different parts, little more, part wise it's explained here. For the parts of the wind turbine in details.